It doesn't work to use this proportional report. It's probably just unstable.
What was it?
When I use PV, it's kind of like
Which is based on
that's what I get.
I can just
Okay, I guess we can get started now. Does anyone have any concerns about the project or the seminar coming up in a few weeks? Any questions about any expectations or anything? Yeah.
I don't have any concerns, but could Tony and I talk to you at the break about that? Just because we're not doing robot, I just wanted to get an idea of what you want to see.
Yeah, but you're doing something that's so close to the robot that it's almost identical to the robot, so
Okay.
I don't think it'll be very much different for you. But yeah, come and talk to me. Anyone else? So last week we were looking into nonlinear control for the first time in the course, and the idea last week was first of all, things are slightly trickier when you have a system in canonical form. You have like x1 dot equals x2 and then x2 dot equals some expression with a lot of nonlinearities in it. So we looked at a couple different ways of dealing with that because it's a little more tricky than just a single input, single output. You know, x dot equals f of x plus u kind of system. But the other thing we were looking at last week was the idea that you can try and cancel out nonlinearities. So you have a control. The camera's already running there, Rachel. We borrowed an SD card already. And yeah, so you can try and cancel out nonlinearities, but you have to keep in mind in nonlinear control that you can't cancel those nonlinearities exactly, and that's really important. In linear control, it's not, you don't worry about it, because in linear control systems, they're basically essentially inherently robust to uncertainties. So in a linear system, if you designed your control based on a model of a system, and your model wasn't really correct, it wasn't really the same as the real system, in linear control, all you would do is turn up the control gains to correct for that discrepancy. That would be a simple fix. So in linear control, it's not a big deal. In nonlinear control, even those little discrepancies between your model and the real world system are really important because they can cause major damage. So the nonlinear controls aren't inherently robust to those kind of uncertainties. So you can't just assume you can cancel out a nonlinearity because you know it. That's always a bad assumption. So in the last class, we looked at what happens when your discrepancy between your model and the real world is just kind of small. So you just have a little bit of error there. Well, what we saw is we could make the controls robust to that little bit of error. So we looked at discontinuous robust controls, and if you can apply that discontinuous robust control kind of truly discontinuous, and you have a good measure of your uncertainties, then you can see we could still get asymptotic stability in the system. And then we saw that we could smooth that out a little bit so it wasn't so discontinuous at the origin if you didn't want to, if you're worried about how the actuators were going to handle that kind of signal. And then you get uniformly ultimately bounded signals. We also looked at nonlinear damping, where we can take terms to like an exponent. And so in that case, the control will grow kind of away from the origin, but it'll grow fast when you get away from the origin in that it'll make things robust to uncertainties. But you still get uniform ultimate boundedness. And then we also looked at optimal control, where sometimes those nonlinearities might actually be helping you, so you don't actually want to cancel them out. So you can just kind of leave them be and let them do their thing if they're actually helping you get to where you want to go. So today we're going to talk about more what happens when your uncertainties are quite large. So if you don't know, this is the nonlinearities, and there's quite a bit of uncertainty there, then you're going to have to go to adaptive control rather than robust control. And these things are kind of mutually exclusive. You can use both adaptive control and robust control. So adaptive control, this is more what you do if you really don't know something. So let's go and teach by example again. Last time I was kind of teaching by example with the robot example, so let's continue that kind of idea. So let's talk about this parameter d in a robot where it's the coefficient of friction. So what we want to do is we want to design an estimate for d, which we'll call d hat, and specifically we want to design an estimate update. So we want to update that estimate somehow. So we're going to define the parameter d tilde, which is little d minus d, little d hat, or little d hat. I'm just going to put all my unknowns in a vector. So I'll just assume d was a diagonal matrix of friction coefficients in the dynamics. So we'll just make little d the vector of all those coefficients. In this case, d hat is the estimate. So note here that the vector d is unknown. So those are my true friction coefficients. I don't really know them. So I'm going to design what's called an adaptive control Lyapunov function. So anytime I use the phrase control Lyapunov function or adaptive control Lyapunov function, that means you're writing down v, but you don't know that what v dot is yet. But you're going to try and make v dot less than 0 with your control. So this is a positive definite and decrescent adaptive control Lyapunov function. And my constant beta here is a positive constant adaptation gain. So that's going to determine how fast the adaptation for d hat occurs. So this is going to just follow basically the same thing I was doing in the last lecture with the robot dynamics. So remember in the robot dynamics last lecture, I was dealing with a nonlinearity f that was m times lambda e2 plus c lambda e2 e1 minus x2 desired minus m x2 desired dot, right? So just for the purposes of teaching this stuff, I'm kind of assuming I know f of x. In reality, I have to use all these techniques for dealing with f x as well, make it either robust or adaptive to uncertainties in f. But just for teaching purposes, we'll just look at D for now and kind of assume we know the rest of the dynamics. So in that case, what we ended up with was V dot equals Z transpose F minus dx2 plus U minus plus 1 over beta d tilde d tilde dot So if you look at the way I defined d tilde, you can see that I can replace d tilde dot with d hat dot because d is an unknown constant parameter. So its derivative is 0. It's not changing. So the thing we're trying to find out isn't changing. So I'm going to rewrite this slightly with a capital X2 here. So I'm just kind of rearranging those terms a little bit. Actually, let me not do that yet. Actually, that's probably too confusing. I'm trying to do 2 steps there at once. So let's just make this a little more understandable. I'll just divide that into 2 steps here. Because I wanted something multiplied by this vector d tilde, but I had something multiplied by this matrix, capital D tilde. And doing that allows me to rewrite this equation like this. So the basic idea here is that in this bracket, now I have known terms. So remember, I'm assuming I know f for now for illustrative purposes, although in reality I want to deal with uncertainties in f as well. Now I have d hat here, which is actually a known. This is my parameter estimate that I'm working with. So this is my estimate for d, so I know this. So I can deal with this term, so I can cancel these 2 terms out if I want to. And then over here, the general idea is that I can design d hat dot to make this whole term go to 0. So I can just kind of make this disappear, and I just end up with whatever I want here. Now it's not quite that simple, as we'll see, but let's just, for now, we'll just kind of pretend it's that simple, and then we'll see how you actually have to really do it. Okay. So I'm going to choose u equal minus f hat plus d hat x2 minus kz, where k is a positive constant term. And my parameter update, d hat dot equal to negative beta xt transpose z. So just for example, my first one, d hat 1 dot, would be equal to negative beta z1 times x2 1. Okay. Yeah, that's right. So just remember we're dealing with like an n-link robot. So when I'm numbering these 1 through n, I'm talking about the links. So this is talking about z for link 1 and x2 for link 1. Can I write that? So then if f hat equals f, then what I get is v dot equals z transpose f. Negative z transpose kz, which looks pretty good. So, because what is this here? What kind of quality does that have? Or a v dot? You conclude v dot is what? Yeah, it's not negative definite, but good guess. So close. So if it's not negative definite, what is it then? By process of elimination.
Negative semi.
Yeah, so it's negative semi-definite. So we kind of looked at this tricky situation earlier on in the lectures, where your v dot kind of looks like it's negative definite when you first look at it, but here it has only a z in it, and it doesn't have the d tilde. So I had a d tilde in my v. So v is a function of z and d tilde. V dot is only a function of z. So that means that it has to be negative semi-definite, not negative definite. Okay, but still, it looks okay. It looks pretty good so far. And we can kind of analyze things that are negative semi-definite with the Lyapunov-Lake lemma. So it's not such a bad. It doesn't look so bad so far. But I'm just going to note right now that this is a very bad idea. And it's not so obvious right now, but we're just going to keep that in mind and look at why this might be a bad idea. But I'm just going to keep on analyzing it with this negative semi-definite result, but just keeping in mind that I don't actually want you to do that. So don't kind of look at this section of your notes and say, this is how I'm going to do my project. Okay? So let's apply the Lyapunov-Lake lemma. The Lyapunov-Lake lemma says that v dot goes to 0 as t goes to infinity when I have a v dot that's negative semi-definite and continuous. So that will imply that negative z kz goes to 0 as t goes to infinity. Z goes to 0 as t goes to infinity. So therefore, d hat dot goes to 0 as t goes to infinity. I.e. state error goes to 0. And parameter estimates go to a constant. Okay, so I'm not actually learning the parameters. It's not a learning system, it's an adaptive system. So the parameter estimates change until your error goes to 0, but it doesn't mean they're correct when the error goes to 0. So they're still going to be wrong. So you haven't learned the correct system, but you have made the error go to 0. So that's why it's called adaptive. That's why it's not called a learning system. Okay. So note, we didn't do anything wrong in the math. So this works in computer simulation. So if you try it out in MATLAB, it'll work fine. It does not work in real life. Basically because,
Chris,
yeah.
sorry, can you explain one more time why it is you call it adaptive, not learning process?
So d hat dot goes to 0, d hat dot goes to 0, but the error, d tilde doesn't go to 0. So d tilde, so if the system was learning, d tilde would go to 0, because that would mean my parameter estimates would converge to the correct values. But that's not the case. Okay, it just goes to a constant. So let's examine what happens in real life now. So this will work in MATLAB just fine. Doesn't work in real life. It's an important thing to keep in mind. So we have to fix this somehow so it does work in real life. Okay, so rather than do this with the robot, I'll just go and do it for a bit more generic system so it's a bit more clear. So let's just look at a more generic system here. X dot equals f of x plus gu plus d of x and t, where d of x and t is a disturbance. I know it's a little confusing because I was using little d to be a parameter estimate in the last example, so d is not changing its meaning. So just make a little note for that for yourself in the notes. So this is basically the reason that it's not going to work in real life, because what I wrote up on the board before was basically I did this for the robot, but I didn't include any disturbances that occur in real life. So because in linear systems, you don't really have to include these disturbances when you analyze stability and stuff. Like I said, linear systems are basically inherently stable to these kind of disturbances. But now we're into a situation where we don't have something that's inherently stable to these little real-life disturbances anymore. So we actually have to take them into account. So we must establish, first of all, that the disturbances are bounded. Or it's not going to work at all. So we have to have the magnitude of d of x and t being less than or equal to d max for all x in some region d, where d max is a positive constant. we can do b equals 1 over 2g x squared plus 1 over 2 beta p tilde p, where p tilde is my parameter error, vector error. So a vector of parameter errors in my system, and f of x over g is equal to gamma p is equal to gamma 1, gamma 2, gamma m, p1, p2, all the way down to pm. For each gamma 1 is a nonlinear function. So for example, if I had f equals a sine x, then I'd have gamma 1 equals sine x, and I'd have p1 equal to a. So you can kind of see the limitations of adaptive control right away, because if I have like sine ax, I can't do this. So we call this, we say the nonlinearity is nonlinear in its parameters. So linear in parameters, meaning you can just take the parameters that are unknown and multiply them by your nonlinearities. So in that case, we'll have v dot equals x, f of x over g plus d of x and t over g plus u plus p tilde transpose p tilde dot. And because the parameter vector is constant, only p hat changes. P doesn't change. So we have p tilde dot equal to 0. Or sorry, equal to negative p hat dot, not 0. P dot is 0. So if we choose u equal to minus gamma p hat minus kx, then we get v dot equal to or sorry, I should write one more line here. Make it a little more clear. V dot is equal to x gamma. Oops, did I screw this up? No, I didn't. Sorry, it's x gamma p plus d of x and t over g plus u minus p tilde transpose p hat dot. Oops, I forgot my beta over here. And so then, if I choose u to be minus gamma p hat minus kz or kx, because I don't know p, then I get v dot equals x gamma p tilde plus d of x and t over g plus u minus p tilde transpose p hat dot over beta. So if we choose p hat dot equal to beta gamma transpose x. And we get v dot is equal to x d minus k x squared. So remember when I did the robot example, I didn't take any disturbances into account. So at this point in my derivation for the robot example, I had a minus z transpose kz, which was negative semi-definite. So this term here is negative definite, but this term could be positive. So now obviously you see when we take real life into account, things might be bad. So I can say v dot is less than magnitude of x times d max, because I know bound on d, minus k x squared. So v dot is less than 0 when x is greater than d max over k. So that might look at first glance like it might be uniformly ultimately bounded. The trouble is that there's only x in that expression there. There's not d tilde. And there is a d tilde in my v. So if I look at x and p tilde, the p tilde plate, so I have a region here. And if x, the magnitude of x is greater than this number, I'll have v dot less than 0. Okay. So what happens here is I have an initial condition, and yeah, v dot is less than 0, so I will go downhill initially. But then I hit this region where I no longer have v dot being less than 0, and I can go off to infinity. And because I can go off to infinity up there, I can eventually come back and hit this dotted line here, in which case I would follow a Lyapunov surface up to almost infinity. So it's an unstable controller. So that the error might go small for a long period of time, but then eventually, because the parameters keep growing, it'll make your error increase quite a bit. So this is usually what's called bursting. So your system looks like it's doing well for a long period of time, and then kind of out of the blue, in a very surprising way, it goes unstable. So if you had been looking at your parameter